Okay, so let's recap what we did last time. Can you hear everyone? Okay, and also ask questions, interact, all of that. So we saw what ring theory is. We started with integers. We saw different properties of integers. Can add, multiply, they're closed under addition, multiplication, they're commutative, distributive law. All of that we saw. We saw Z mod nz, which was, let's see if you remember. Can you tell me what Z mod 6Z is?
0, 1, 2, 3, 4, 5.
Yeah, 0, 1, 2, 3, 4, 5. Then what's Z mod 7Z?
0, 1, 2, 3, 4,
5, 6. Yeah, okay. This is how you can add stuff. You can, in Z mod 6Z, what's 5 plus 6?
5.
It's 5 because it's 11, the remainder is 5. We saw all of that, and then we saw Z adjoined X. Okay, yeah, we saw Z adjoined X, which was polynomials with integer coefficients. And again, we saw all of those properties, and then in place of X, we put I and root D, and then we saw if you put I, you get something of the form A plus BI. And then if you put root D, you get something of the form A plus B root D. And then again we saw all those properties. Then we saw rational numbers. In rational numbers, one more interesting property was every non-zero number had an inverse. It has an inverse. And next we saw quaternions. Okay, then we saw ring theory.
Can you recap what quaternions were?
Okay, sure. It's numbers of the form A plus Bi plus Cj plus Dk, where AB and ABCD are real, CD are real, okay, and I, J, K are I squared equal to J squared equal to K squared equal to -1. In fact, I learned a few days ago there are stuff called hexternions, where there are 6 such terms, and then this helps to visualize 3D motion, and then octernions help to visualize, this helps to visualize 2D motion, octernions help to visualize 3D motion.
Octernions are 4 dimensions.
8. Yeah, I mean 8 such terms.
8 such terms.
Okay, and you see that complex numbers, this is just a complex number, and complex numbers can in fact represent 1D motion. Okay, so then we saw those properties. We saw what a ring is. A ring was basically a set of elements. It had 2 operations, plus, into. It was closed under multiplication. Addition was commutative. There was an identity, inverses, all of that. Then we saw why negative into negative is positive. Yeah, we saw the types of rings. A commutative ring is where multiplication is commutative, integers, rational numbers, all of that. An integral domain is where AB equal to 0 implies A equal to 0 or B equal to 0. We saw one example where that was not true. Which example? In Z mod nz. Yeah. 2 into 3. What's Z mod 6Z? What's 2 into 3?
It's 0.
It's 0. So 2 into 3 is equal to 0. 2 is not 0, 3 is not 0. That was an example of a non-integral domain. Then we saw division rings. Everything has an inverse. Then we saw fields, which are integral domains and division rings at the same time. Then next, yeah, we saw what a unit is. Unit is like 1. It divides everything, and this was a more formal definition. A ring is, an element is a unit if there exists V such that UV equal to 1. We saw different units, and then next we saw 0 divisors. As I said, 2 and 3 were 0 divisors because they were units. Sorry, they were not units, they were 0 divisors because 2 into 3 was 0. We saw divisors in the ring, it's like just like integers. Next, primes, same thing. And UFT is wherein this thing, like the fundamental theorem of arithmetic is followed, where you can break down, let's say, 12 into 2 squared into 3. That's the only way you can break down 12 into product of primes. Next. Okay, yeah, we're done with the recap. So now let's come to today's talk. Today, for the first around half an hour or so, we're just going to talk about stuff you actually know about already. Look at that. We started off with division. So let's take 15, 7, you get 14, 1. Then people saw that you can write 15 as 7 into 2 plus 1, right? This is your division. We've been doing this since third standard. So now 15 is equal to 7 into 2 plus 1. So they started to call 15 as A and B, Q and R. So A equal to BQ plus R. So that means if you take any integer A, any integer B, you can write A as BQ plus R, where R is less than or equal is less than B and greater than or equal to 0. This condition imposed that Q and R must be unique. So when you divide 15 by 7, the only quotient you can get is 2. The only remainder you can get is 1. So
Why can't we get negative remainder?
greater than 0.
Yeah, why do we have that?
Because then this won't be unique.
Okay. In the sense?
In the sense, now you can add something negative here, right? No. Now you can take 7 3s are 21. 15 minus 21 is negative 6. You get one more thing. Similarly, you can do 7 4s are Q and R don't become unique. Then with the help of this, we saw how to find HCF, right, using something called Euclid's division algorithm. So 15 and 24. 15 and 24. What is HCF?
Highest common factor.
Yeah, greatest common divisor, HCF, same thing. 3. So I'll take one, 72 and 63. What's the greatest common divisor? It's 9, right?
Oh, 9.
Yeah, it's 9. Okay, fine. So this is, for these questions you can eyeball it, but then for larger numbers they developed this method called Euclid's division algorithm. So basically you look at 15 and 24, you see that 24 is equal to 15 into something, right, plus something. That was the A equal to BQ plus R thing. 15 into 1 plus 9. And then you got the 15 here is equal to, you got the 9 here, 9 into 1 plus 6. Then you got 9 equal to 6 into plus 3. Then you got 6 equal to, yeah, plus 0. So now that you got 0, you conclude that this is the HCF. I'll do one more example. Let's do the let's take 21 and 60. No, that's a multi. 21 and 49. What's the HCF just by eyeballing? 7. Yeah. So try calculating it like this. So what do you do first? What do you, yeah, 14, 21 into 2 plus 7. Yeah, 21 equal to 7 into 3 plus 0. Hence 7 is the HCF. Now that was Euclid's division algorithm, and then I write these steps down again. 15 into 1 plus 9. Okay. Now then we learn something called Bezout's lemma, wherein you go backwards here. Click. The statement was that you can write if you have the GCD or the HCF, it was 3 here, so 3 is equal to 15 into something plus 24 into something. That was the statement of Bezout's lemma. You can always do this. How do you actually do this here? Okay, let's start with this step. So you have 3 equal to 9 minus 6 into 1. Now 6 is equal to 15 minus 9 into 1. So you can write this as 15 minus 9 into 1 into 1. The into 1s don't matter. Then you can again see that 9 over here. Wait, yeah, it's 15 minus 9. Yeah, that's correct. Okay, anyway.
Substitute for 9. Then you get it.
Substitute for 9, 24 minus 15 over here, and minus 24 minus 15. You get 30. Wait, I made a mistake.
15 minus 24.
Yeah, I made a mistake. Sorry. You start from here. 9 minus 6 into 1. You write 6 as 15 minus 9 into 1. 9 minus 15 into 1. Sorry, 15 minus 9. Then 9 minus 9, you get 0 plus 15. Yeah.
Minus of minus 9.
Minus of minus 9, yeah, you get plus 9. Oh yeah, okay, you get 15 plus 9. Negative 15 plus 9.
Yeah, negative 10
Okay, then
plus 18, right? 9 plus 9.
plus 18. Ah, come on. 9 into 2.
Yes.
Then for 9, you substitute 24 minus 15 into 1. 15, negative 15 plus 24 minus 15 into 1 plus 24 minus 15 into 1 into 2. You get this as 2 times 24, and then you get a minus 2 times 15 plus minus 15 minus 2 into 24 minus 3 into 15. This is 3. I'm sorry for that, I haven't done it in a long time. You can check that out for other numbers too. But yeah, that was the crux of it. You can always write it in such a way. So now the next thing we are going to look at, we are going to return back to this. The thing is, the actual proof, like for y3 can always be written as 15 into something plus 24 into something. Here we had a numerical example, we could just go back. But in general, if you have a, b, x, y and d, so you have a and b, the GCD of a and b is d. You can always write it as ax plus by equal to d. That's not an obvious thing, you have to prove it. The number theory proof is really long. So based on what we did last time, rings, right, we're going to define something inside a ring which will help us prove this in a better way. This might sound a bit dry now, but when Rishon and Lauren come up and give their, they'll give more examples, right? So if you don't understand this, there's not a it's important foundation for what they're going to teach, and what they're going to teach is beautiful, some of the proofs they give. Okay, multiples of a number. We've been doing this since, I don't know, 2 1s are 2 2s are, stuff like that. Let's start with multiples of 2. It's 0, 2, 4, 6, 8, negative 2, negative 4. And this is called 2z, right? We had seen it last time. Like I don't expect you to remember it, because even I have forgotten all of this. Fine. This was called 2z. This is just the set of all multiples of 2. What's the set of all multiples of let's say 4? Yeah. Yeah, 4, 8, 12, dot dot dot, 4.
Just multiply every element
Yeah.
of Z with that number.
Yeah, just the multiples of the number, right? This was called 4Z. Now, let's talk about adding these two things. Okay. Normally, when wait, can you click that? Okay. Yeah. Let's talk about adding these two things. Now, while adding, how we add it, it's not the union kind of thing which we do in sets. How we add is we take an element from here, we add it to every single element from here, right? Do the same for all other elements. That's how you add it. Now, if you observe that, try guessing what, just try doing it for a few numbers and try guessing what the set will be. I'll give you one more example. Yeah, try taking 3Z. Okay, no, try taking 2Z itself and add it to 3Z. What is 3Z?
Multiples.
3. What's 2Z multiples of 2? Try doing it for random numbers and seeing like what numbers you can end up at. No, that's wrong. Not for here. You don't. It's not. It's true that multiples of 5 are contained in this, but that's not the set. You can't just add up 2 plus 3 5. Did you? What you're supposed to do is like just take 2. Huh? What? This plus this. No, it's not. You don't get 5Z.
Because you have
No, and also, Abhidnya, for multiples of 6, if you take 2 plus 3, 5, 5 is not a multiple of 6. You're on the right track.
You
Yeah.
add 0, right? But
Yeah.
multiple is
Yeah,
zero.
yeah.
You get the original set.
You get all elements of 2.
Yes. And
You
all
also get all elements of 3. For which one are you talking about? No, you obviously get even odd numbers too. 3 plus 0 is 3. Okay, over here, try doing this. Take 0, you add it to 0, you add it to 4, 8, 12. You get this thing back. Now take 2, you add it to 4, you add it to 0, you add it to this, you add it to this. Yeah, shifting does not matter, right? It's just, it'll always be in the same order, it's a set. So you just get back 2Z. So 2Z plus 4Z is just 2Z. Because you can get back every element of 2 from here also. Now, for this one, if you try doing it for some values, let's just try guessing. 0, it's possible to get a 0. Is it possible to get a 1? How? In this one. This one. Yeah, it's possible. It's possible.
Minus 2, 3. Minus 2 and 3.
Minus 2 and 3. Is it possible to get a 2?
Yes.
4 and negative 2. Sorry, sorry. 5 and 2 and 0. Sorry, my bad. Is it possible to get negative 1?
Yes.
2 and
Minus 3 and 2.
So, if you try thinking of it like that, I mean, at a point, it's not a proof yet, but you just get Z itself. If you add the multiples of 2 with the multiples of 3, you get all the integers. Okay, so one thing to observe here is 4 is just a multiple of 2, right? Yeah, so hence that's why it ended up being 2Z. But here 2 and 3 have no common factors. Okay.
why did it end up being Z?
I will show that later. Multiplying two things. Now your logic works. If you multiply this, this is a 6Z. It's not defined like that. It's not 2Z into 3Z. Multiplication has a definition. It's a bit complicated. You take this and multiply it with an element in this, right? and do that of n number of times.
With which multiple?
Yeah, you can have any number of such combinations. Okay, it's sigma ai bi, where ai belongs to b and ai belongs to this set and bi belongs to this set. Yeah, you can try doing that actually. I won't do it here. I already have a lack of time. So that ends up giving you 6z. So you can multiply like that. Then next, divisibility. Oh, okay. This I found interesting. Look at how you think of it like this. 2 divides 4, right? 4 is 2 into something. 2 into 2, yeah. So 4z is also 2z into something. So you can think of it as 2z divides 4z, right? All the multiples in here divide this. Now, what does this actually mean? This means that this set is contained in this set, right? Yeah.
But it doesn't mean like it divides each one of them.
Yeah, it does not mean each. It's like a definition right now. No, wait. Yeah, but 2 divides everything here. Okay, yeah. What this actually means is 2 is a superset, or we can say 4 is a subset of 2. The multiples of 4 are the subset of the multiples of 2. Isn't that's kind of obvious, right? Multiples of 4 are the subset. Similarly, 3z and 6z, right? 6z, the multiples of 6 are just a subset of the multiples of 3. Yeah, so that means the way we define this is if a multiple of some number a, right? If this set divides the multiples of some number b, this is just a denotion, right? This means that b is a subset of a. This is the symbol for subset. All elements in b are in a. Okay, next. Okay, GCD of multiples, we'll look at that later. We already kind of saw that. Anyway, next. Okay, yeah, even this I found it really interesting. Now here you found the multiples, right? Now try thinking of z mod 12z. Okay, what is this? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now over here, take an element. Let's say 2. Okay, I'll write down the set here. This is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, z mod 12z. Now the multiples of 2, what are these? In this set, what does this mean? You take 2, multiply it with every number in the set. Yeah, that's right. So you take 2, 0, 2, 4, 6, 8, you get 10, 12. 12, 14, 16, 20. Is that it? Yeah. But then, yeah, 14 is just 2. This is just 4. This is just 18. Yeah. Because 2 is a 0 division. Now, what do you think the multiples are?
0, 5,
10. Okay, that's intuition. 15 is just 3 again. Fine. 0. Let's now multiply. 5 into 0 is 0. 5 into 1 is 5. 5 into 2 it's 10. 5 into 3 15. 15 is 3. Even 3 is also a multiple. Okay. 5 into 4 20. 20 is just 8. 8 is also a multiple of 5 in Z mod 12Z. 5 4s are 5, 5s are 25. 25 is, wait, what? 3, 8. Then 25 is just 1. 5 into 5. 5 into 6, 30. 30 is just 6. Okay. Then 30, 36. This is, sorry, 5, 6 are 30. 30 is answered. 35. 35 is just 11. So you end up saying that just gives you the original set. I'll do the entire thing. What's 5 into 8?
40.
What's 40?
47.
What remainder does it leave?
Yeah, what remainder when you divide by 12?
4.
Yeah. Then 5 into 8 and 5 9
45.
45. What's the remainder?
9.
9.
9. Then 5 into 50.
2.
5 into 55. 5.
7.
7. So now, let's check. Do we have 0? We have 0. We have 1. Yeah, we have 1. Do we have 2? Yeah, we have 2 over here. Do we have 3? We have a 3. Do we have a 4? Yes, we do have a 4. Do we have a 5? A 6? Upwardly written 6, but 1. 7. Where was 7? Yeah, the last one. 8, it's over here. 9, it's there over here. 10 is there over here. And 11 is here. So you just get back the same set. And now, if you go back to the old thing, 2 was a 0 divisor in Z mod and Z, based on the things I taught last class. So that means 2 into 6 equal to 0. 2 6 are 12. So that's why 2 was called a 0 divisor. And why this was true? Because 2 and 12 have a GCD which is 2, which is not 1. And then if you take 5, the GCD of 5 and 12 is 1. And based on what you saw last time, if that's true, it's a unit. Okay? And then think about it in integers. What are units in integers? 1 and negative 1 also. What happens if you take all the multiples of 1?
You get what real number.
Not real numbers, integers. Yeah, you get all the integers if you take multiples of 1, right? Even here, 5 acts like a 1. It's a unit. It does not act like 1, but it's a unit. So when you take the multiples of 5, you'll get the entire set, right? So that was one of the things in Z mod and Z. There are other numbers, yeah.
Can you explain how this 5 into 3 is
5 into? Okay. 5 into 3 is 15. What is 15? What's the, remember we care only about the remainders when you divide by 12. What is the remainder when you divide 15 by 12? 3. Hence I put 3. There are other number systems, ZX, all of that. I won't be doing all of that today. I think Rishan or Lauren, one of them will go into detail about that. Okay, so we saw different properties, right, of these multiples. So then we thought, how do we generalize this idea of multiples? So we called something, we defined something called an ideal. You can choose whichever definition you like. I mean, basically what an ideal is, okay, you can read it. It looks complicated, but okay, so yeah.
Why do you divide by 12?
Why do that's the way how this set is defined. In the last talk we saw what Z mod NZ is. You care only about the remainders. Okay, so basically if you ignore all of that, what this actually means is if you have a ring, let's say integers, and you take a subset of the integers. Let's say we had z, we took a subset of z, which is 2z. Now, the interesting property of 2z is that 2 into any number in that larger set z will give you an element in 2z itself, right? If you think about 12, right, 12 into any element in z will give you an element in 12z itself. So that's how the ideals were defined. This definition, it was a non-commutative thing, because 12 into 1 would not have been the same as, sorry, not 1, 12 into let's say 3 would not have been the same as 3 into 12. Hence this definition was given. But in general, it's like, if you can think about it as just multiples of a number. If you tell ideals, it's just multiples of a number. And by the end of the series of talks, you'll think of ideals not as sets like I'm defining now. You'll think of them as numbers. You'll start adding them like numbers, things like that. That's so. Don't think of the word ideals too much. It's just multiples. Okay. In fact, how the word ideal came is, it's related to the story I told last time, but I won't be covering that. I think Rishan. Basically, this guy was Kamar. Yeah, format. Yeah, it was based on format. Like, this guy was trying to think of some ideal number, hence he started calling such things ideals. Okay, next. Yeah, principal ideals. This is just a big, since the way we defined an ideal was as multiples, it seems obvious that every ideal is a principal. What's a principal ideal is just the definition I gave you. You can read it. It's just what I told right now. It's just multiples. It's just like notation for multiples of a number. Anyway, you might ask, if you had defined ideals as multiples, why principal? Because you can define ideals using, let's say, two elements. Like in polynomials containing z, I mean polynomials with integer coefficients, this is also an ideal, like x squared minus 1 comma x, let's say. What this is called, even this is an ideal. What this actually does is, you take all the multiples of x squared minus 1, which is just x squared minus 1 into f of x. Then you take all multiples of x plus x into g of x and add them. This was the definition of x squared minus 1 into x. But it turns out that this itself is not a multiple of some other polynomial. So it was not a principal ideal, because you couldn't write every number in this as a multiple of two other polynomials. Okay. So then prove that A is an ideal. That comes out of the definition right now, so we won't do that. Prove that A is a unit if and only if A is the entire ring. We saw that with Z mod 5z. I won't prove that. What's the time? Okay, yeah. Prove that every ideal of Z is a principal ideal. It's a proof. If you want to know more about ideals, ring theory, you can just binge watch this Michael Penn. In fact, watching this will help you for Rishan's talk and Lauren's talk, which I think is next week. Okay, next. Operations on ideals. We already saw addition. We saw what divides means. We saw multiplication. We did not see what a prime ideal is. But in integers, if you take all the multiples of a prime number, it turns out it's a prime ideal. Again, if you want more information, you can refer the internet. Prime ideals is defined as, if you have, let's say, A and B, an ideal P, again this is notation, it's prime if P divides A into B, where A into B is that multiplication there, implies P divides A, P divides A or P divides B. It's P, yeah. This is the same, similar to the things we learn in integers. That's how P divides AB means P. But why it's written like that over there is, you remember I told you that time, A divides B means B is a subset of A, right? So that's the same thing here. AB is a subset of P means P divides AB. P divides A or P divides P. Then we saw how to add. We took 2z, 4z, 2z, 3z. We saw multiplication. Okay, this is the thing that I actually want to do today. So if you saw that time, 2 and when you took ideal 2 and added it to ideal 4, you got the ideal 2 back. Now what's the GCD of 2 and 4? 2. If you took ideal 2 and ideal 3, you get the ideal 1. 1 is just the entire set. What's GCD of 2 and 3? 1. So 3 and 6, what do you think you'll get? 3. Right, so in general, I plus j equal to GCD of I and j. I and j are ideals here. Okay?
Could you generally prove it?
Yeah, I'm going to prove it right now. Okay. How do we define GCD of two ideals? The GCD is the largest set, the largest ideal that divides both I and G divides J. That's how GCD is defined. Like normally you can just take the numbers inside, but in general number systems, G divides A and G divides J. It's the largest set that divides both I and J. This also means G divides I plus J. Yeah, okay, this means G divides I plus J. Keep that in the back of your mind. What does this mean? I is a subset of G. J is a subset of G. And in general, this means I plus J is a subset of G. Okay? So, yeah. Hence, I'll write it down neatly. Like, neat in the sense G divides I and G divides J implies G divides I plus J, which implies I plus J is a subset of G. Now, so you got I plus J is a subset of G. Now let's take I and J. You can in fact prove this. I've not proven it here, but I divides I plus J. Okay? This does not mean I divides J, but like I divides I and I divides J, but I divides I plus J because I. Huh? No, you can ask. Huh? Yeah, sorry, my bad. I plus J divides I. Yeah, you can see that. What was 2 plus 4? 2. 2 divides 2 and 2 divides 4. This is true only in this case. Yeah, but 2 divides 4. We saw that time. I plus J divides I. Also, I plus J divides I plus J divides J. Okay. Now we define GCD as G divides A and G divides J. In fact, actually, this means it's the largest, it's the smallest set containing both I and J. If that's because of this moment here. So what does this mean? Yeah. I plus J divides I and I plus J divides J. Now think about this. This is the largest ideal that divides both I and J, and this is another ideal that divides both I and J. So that means I plus j must divide g. What does this mean? G is a subset of I plus j. Now G is a subset of I plus j. I plus j is a subset of G. What does that mean? They're equal. Okay, so I plus j equal to G. Okay. So now you take I plus j. Why am I writing plus? I plus j equal to GCD of I comma j. How can you write this better? A plus b is equal to GCD of a comma b. Now what is a? Like, I mean, what does this mean?
The ideal values.
Yeah, the ideal a. How did we define ideals? Multiples. So this is just multiples of a. These are just multiples of b, right? That's how we defined ideals. So this is a into some r1, let's say, or better, a into x. What is this? B into y. And now this is just GCD of a comma b. Isn't this Bezout's lemma, ax plus by equal to GCD of a comma b? So basically this is all we had to do. Like, the proofs are, we don't have to do the proofs. These are just the 3 steps to prove Bezout's lemma. Now ideals was not developed only for proving this. It was developed for way more interesting reasons, as you will see in the next talk, that is Rishan's. But I just wanted to give the introduction to ideals, and yeah, we're done for today. Thank you.